The RADICLE project is a 3-year Horizon 2020 program. The word RADICLE itself actually stands for real-time dynamic control of laser welding. The idea being laser welding is a very high investment technology. It's got a lot of process advantages to it, one of which is mainly speed and heat input, but it's got a very fine processing sort of window. It's very new, and as a result, a lot of companies that could invest in this technology they're quite fearful of it, and rightly so. It is prone to defects like any other welding process. So although it's this miraculous process that can offer all these advantages, it still has its disadvantages. Any defect needs to be reworked. That adds more cost to the process, and when we have customers now looking at assemblies or welded fabrications that can cost anywhere from several euros up to €500,000 going on to full assemblies worth 20-30 million euros, you can start understanding that actually there's a requirement to get not only welding right every time, but right first time as well. So it's a big challenge. The MTC led the development of the bid for the RADICLE project. We're now also delivery and technical leads for the project as well. So really we have overarching responsibility for the day-to-day management of the project from a sort of business side and from a technical point of view as well. Alongside our partners in the TWI, we're responsible for a lot of the actual welding work and testing work that's being done within the project. We have other partners including Laser Optical Engineering, who have a responsibility for investigating and developing some of our sensor systems. VTT in Finland are responsible for probably the hardest part in the development of the control algorithm itself, and we also have partners in EWF who are responsible for things like the dissemination and the development of training materials. So if we do have this new system, how can we then release it out into the wild and make sure we have maximum uptake? We then have a whole bank of end users involved on the project, who are the ones really sort of driving this from an industrial point of view and saying, these are our requirements, this is what it has to try and achieve. So it can be a bit of a juggling act, but we're getting there with it. One of the big problems we found with any of the welding work involved on this project is it's very easy to turn around and say, well, this is the set of welding parameters that work for this specific requirement. And whilst that's all well and good, it actually doesn't help the customer develop that technology further for themselves. If they say, actually, I have another product that I'm going to use this process on, how can I then roll this technology out into that if, say, the material thickness is different or it's a different material? Also, there are a range of key process variables which the user can control that will steer how the process works and how well it works. But it's then a case of understanding the relationship between those weld inputs and the attributes of the weld that come out at the end of it. And there's been an awful lot of welding work done by both ourselves and TWI to say, actually, this is the relationship. You change any of these parameters, this is the variation it makes in its output. We then have to work with our sensor partners at LOE to say, each one of these changes, there is a signature that the process emits, be it in terms of other light wavelengths being given off, in terms of process noise, particulate from the process itself. And then we have to learn to relate those signals to our input parameters and to our weld attributes. And then from that way, our partners at VTT can develop the algorithm that should, in theory, tile this together and enable this dynamic control of the process. The interesting thing with the project overall was really it's never been done before. It's been attempted by a number of research groups, and there are a number of systems on the market that claim it can monitor the process. But those systems generally only infer what is happening within the weld, whereas we need to be able to identify what's happening in the weld, quantify it, and then we can adjust for it. So it's been a really big technical challenge. At the end of the project, we hope to have a real-time dynamic control system for laser welding, which is in itself is pretty groundbreaking. The other thing we will also have is a catalogue of welding information covering a range of engineering materials in a range of thicknesses, and this in itself is actually a very marketable and very valuable product because it enables an end user to say, yes, this is my new product, it's made of this, it's this thick, these are the parameters I now need to apply in order to weld it in an optimal fashion. There's been an awful lot of useful identification work done on current welding sensing and detection packages as well. Some of these are available as just individual standalone sensors. Some have been supplied or can be supplied as a complete standalone system. And it's also then being able to tell industry, actually, this is the capability of what these systems can do. It's very easy for a system manufacturer to say, this is what our system does, but actually what the end user can do with that may be slightly different. So we're here to kind of make that understanding more clear for the end user.